Assalamualaikum. In today's episode, we consider one example, the application of the second law of thermodynamics, the working principle of an electric freezer. Specifically, we will talk about the freezer's coefficient of performance, or its ability to extract heat from the cold reservoir to the hot reservoir. So just stick around, watch, and learn. The question is, a freezer has a coefficient of performance of 2.40. The freezer is to convert 1.80 kilogram of the substance water initially at 25.0 degrees Celsius to 1.80 kilograms of ice at negative 5.0 degrees Celsius in a period of 1 hour. Question letter A. What amount of heat must be removed from the water at 25.0 degrees Celsius to convert it to ice at negative 5.0 degrees Celsius? Question letter D. How much electrical energy is consumed by the freezer during this period of 1 hour? Question letter C. How much wasted heat is delivered to the room in which the freezer sits? First thing first, we are given the following data and information. The coefficient of performance of the electric freezer, or COP, is equal to 2.40. We consider a mass of liquid water denoted by N sub W equal to 1.80 kilograms as the thermodynamic system. Initially, at a temperature of T sub 1 equal to 25.0 degrees Celsius, we place it in an electric freezer until the substance freezes at a final temperature T sub 2 equal to negative 5.0 degrees Celsius. And the period of time we consider for the whole process is 1.0 hour. We also emphasize here the following constants that we need in our computation, such as the specific heat of the liquid water, or C sub W equal to 4,184 joules per kilogram per Celsius degree. Also, we have the latent heat of fusion of ice, denoted by capital L sub F equal to 3.36 times 10 to the fifth power joules per kilogram, as well as the specific heat of ice, denoted by C sub I equal to 2090 joules per kilogram per Celsius degree. And our target variables include, for part A, the amount of heat QC extracted from the cold reservoir. And in part B, the amount of electrical energy, right, that is consumed by the freezer in a period of 1.0 hour. And in part C, the amount of wasted heat that is delivered to the room in which the freezer sits, also known as the hot reservoir. Moving on to our computations, in part A, we find the amount of heat that is extracted from the cold reservoir, capital Q sub C, and it's just equal to the sum of Q1 plus Q2 plus Q3. Okay, starting with Q1, which we define here as the amount of heat extracted from the liquid water to cool it down from 25 degrees or 25.0 degrees to 0 degrees Celsius. That is, Q sub 1 is equal to 1.80 kilogram multiplied by 4,184 joules per kilogram per Celsius degree times 25.0 Celsius degree. All right, this is the difference between 25.0 degrees and 0 degrees Celsius. So when we do our math, we find the value of Q sub 1 equal to 2.03 raised to the fifth power joules in three significant figures. For Q sub 2, which is the amount of heat extracted from water, okay, at 0 degrees Celsius for it to completely freeze. And that is just equal to the mass of the water and the constant known as the latent heat of fusion. That is, Q sub 2 is equal to 1.80 kilogram times 3.36 times 10 to the fifth power joules per kilogram. So, multiplying, we get the value of Q2 equal to 6.05 times 10 to the fifth power joules, also in three significant figures. For Q sub 3, which is the amount of heat extracted from ice for it to drop its temperature from 0 degrees Celsius to negative 5.0 degrees Celsius. And Q sub 3 is just determined by multiplying its mass, the mass of ice, times its specific heat and the change in temperature delta T. That is, Q sub 3 equals 1.80 kilogram times 2090 joules per kilogram per Celsius degree multiplied by 5.0 Celsius degree. That is the value of delta T. So, again, when we do our math, we find the value of Q sub 3 equal to 0.188 times 10 to the fifth power joules, also in three significant figures. All right? So, we can now therefore find the value or the amount of heat QC, which is just the sum of Q1, Q2, and Q3, or Q sub Z equals 2.03 times 10 to the fifth joules plus 6.05 times 10 to the fifth joules and plus 0.188 times 10 to the fifth joules for a total of 8.27 times 10 to the fifth power joules. All right, so this is the amount of QC, or the total amount of heat that is extracted from the cold reservoir. In part B, we can find the amount of electrical energy, capital E, that is consumed by the freezer, all right, in a period of 1 hour. So we will assume that the amount of energy, electrical energy consumed by the freezer is equal to the work done, all right, W. This is the work done by the compressor of the freezer, okay, in order to extract the heat from the cold reservoir. So the work done by the compressor of the freezer is just equal to the amount of heat that is extracted, okay, from the cold reservoir, or QC, divided by the coefficient of performance of the freezer, or COP. That is, this electrical energy consumed equals 8.27 times 10 to the fifth power joules. That's the value of QC, and then divided by 2.40, the value of COP. So we get the amount of electrical energy consumed by the freezer equal to 3.45 times 10 to the fifth power joules. And take note that this amount of energy consumed by the freezer is for a period of 1.0 hour. And you might be wondering how large or how small this amount of electrical energy consumed is. Recalling that in 1 kilowatt hour, we have 3.6 times 10 to the 6th power joules. So when we convert 3.45 times 10 to the fifth power joules to kilowatt hour, we find that that is equal to 0.0958 kilowatt hour. And finally, moving on to part C, that is determining the amount of heat that is expelled into the surrounding, right? Or we also say that this is the amount of heat that is transferred, all right, or expelled to the surrounding in which the freezer sits, all right? That surrounding is also known as the hot reservoir. And it is determined by simply adding the amount of capital Q sub C and the electrical energy consumed, or Q sub C plus capital E. That is, Q sub H equals 8.27 times 10 to the fifth power joules plus 3.45 times 10 to the fifth power joules. So the value of QH in three significant figures is equal to 11.7 times 10 to the fifth power joules. So obviously, the amount of heat expelled to the surrounding is indeed much greater than the amount of heat that is extracted from the cold reservoir or the freezer itself. And in addition, we say that the useful work done by the compressor of the freezer is pretty less than the heat that is extracted from the freezer. We say therefore that the freezer's coefficient of performance, which is 2.40, represents the ratio of the heat that is extracted by the freezer from its contents, such as the water, right, in the cold reservoir, Q sub C, to the energy or work done by the freezer's compressor in expelling this heat to the surrounding, right? Higher value of COPs equate to a higher efficiency, lower energy or power consumption, and thus lower operating costs. And that ends our lesson for this topic. Till the next episode. Mabuhay. MashaAllah. Thank you very much for your indulgence. Please don't forget to subscribe to my YouTube channel. Alhamdulillah.